Hello all, myself Shruthi, lecturer in physics, SVSC College Bantoy. Today I am going to discuss about superconductivity, second B.Sc topic as prescribed by Mangalore University. The field of superconductivity has emerged as one of the most exciting fields in physics because of the nature of the phenomenon and also of its immense applications. Superconductivity was discovered in 1911 by the Dutch physicist Hij Camerlingens. He won Nobel Prize. He was working in his cryogenic laboratory at Leiden University. He found that the resistance of mercury sample decreased with the temperature, and at 4.15 Kelvin the resistance fell sharply and reached zero. Similar results were obtained by using various other metals. So the conductivity is nothing but the phenomenon of disappearance of electrical resistance, and this particular graph shows the variation of resistance of mercury sample with temperature. As temperature decreases, the resistance of the sample also decreases, but at one particular temperature resistance fell sharply and reaches to zero, and this particular temperature is called critical temperature. So the critical temperature of mercury sample is 4.15 Kelvin, or mercury is superconductor below 4.15 Kelvin. This is also called as critical temperature is also called as threshold temperature. Now what is the definition of critical temperature? A particular temperature below which the material shows superconductivity. And in this state, the materials are called superconductors. Elements which are ordinary good conductors such as copper, silver, iron, etc. do not become superconducting when it is cooled because they do not form Cooper pair. What is Cooper pair? I am going to explain in the next slide. For intermetallic compound Nb3Ge, critical temperature is 23 Kelvin. Critical temperature is denoted by Tc. For bismuth, critical temperature is 180 Kelvin. In this slide, properties of some selected superconductors in chronological order is given. BCS theory, which is very important because it explains the phenomenon of superconductivity in any material. In the year 1957, Bardeen, Cooper and Schrieffer gave the theory which explains the phenomenon of superconductivity. That's why the name BCS theory. According to this theory, the current carrying electron in the superconductor, they interact with the lattice point. During this interaction, they form a bound state. Electrons form a bound state. Two electrons form a bound state, and that is called Cooper pair, despite of their Coulombic repulsion. Here in this process, the lattice get slightly distorted. The positive ion in the electron path get displaced towards it, towards electron. The deformation produces a region of increased positive charge. Another electron moving through this polarized region will be attracted by the concentration of positive charge, but the attraction between the electron is stronger. If the attraction between the electron is stronger than the repulsion between them, they couple together into a Cooper pair. Here lattice is the intermediate. So the lattice vibrations are quantized in terms of phonons. Thus the process is called electron lattice electron interaction via the phonon field. When the electron flows in this form of Cooper pair in material, they do not encounter any scattering. Because of this, the resistance factor vanishes. The electrons in pure metals such as copper, silver, gold, etc., they move freely. They do not interact with the lattice. Because of that, they do not form Cooper pair. Hence, they do not exhibit superconductivity. Now let us see some of the experimental facts of superconductivity. First one, effect of magnetic field. Superconductivity of a material disappear if the temperature is raised. That we know. If the temperature is raised above the critical temperature, the superconductor becomes normal conductor. Similarly, if a sufficient magnetic field is applied, if the magnetic field is exceeds a critical value, in that case also the superconductor becomes normal conductor. That is denoted by critical magnetic field is denoted by B.Sc, which depends on the material and its temperature. So from this graph you can see that inside the curve the material is superconductor, above which the material is normal conductor. So now what is critical field? The strength of magnetic field required to just change the material from superconducting state to normal state is called critical field. Next one, Misner's effect, flux exclusion, or it is also called as flux expulsion. It is also important. It is discovered by Misner. A superconducting material, if it is kept in a magnetic field which expels the magnetic flux out of its body when it is cooled below critical temperature. Only if it is cooled below critical temperature it will become superconductor. And thus it shows perfect diamagnetism. And this effect is called Misner's effect. In 1933, Misner and Ostenfeld found that the specimen like lead and tin at their critical temperature become perfectly diamagnetic, even though they have been cooled in the magnetic field. Inside that means inside superconducting material, magnetic field is always equal to 0. Magnetic field is always equal to 0. Why this happens? Because the current appears on the surface of the superconductor whose magnetic field exactly cancels the original field inside the material. Because of this, magnetic field inside the material seems to be equal to 0. A rod-shaped superconducting specimen therefore behaves like a long solenoid with circulating current that creates flux density exactly equal in magnitude but opposite in direction to the flux density due to the applied magnetic field. In this slide you can see that when the substance is above the critical temperature, they allow magnetic field line to pass through it. If the substance is superconductor, that means it is under critical temperature, they will not allow magnetic field line to pass through it, or it shows perfect diamagnetism. Next fact is critical current. An external magnetic field applied to the superconductor causes a superconductor to normal. If the magnetic field exceeds B.Sc, then the superconductor material becomes normal. But magnetic field arises due to electric field. We know that if there is electric field, it always associates with the magnetic field. So the magnetic field arises due to electrical current flows in the conductor. The minimum current that flows in the sample without destroying its superconducting property is called critical current. If critical current increases, magnetic field increases. If magnetic field exceeds B.Sc, then the superconductor becomes normal conductor. So the current should be maintained such that the surface current should be maintained such that it should not destroy its superconducting property. And that particular current, the range of current, is called critical current, denoted by IC. Surface magnetic field associated with the current is given by, if H1 is a surface magnetic field associated with the current is given by H1 is equal to I by 2 pi r. Here r is the radius of the superconductor wire, I is current in the sample. If H1 exceeds the critical value, material will become normal conductor. Suppose a transverse magnetic field is applied or the perpendicular magnetic field is applied to the wire. Critical magnetic field now becomes the sum of applied magnetic field and field due to surface current. That is, HC is equal to critical magnetic field is equal to H1 plus 2H. Here, if we rearrange this equation, Hc minus 2H is equal to H1. We have expression for H1, that is I by 2 pi r. By substituting that, I is nothing but critical current IC by 2 pi r, or IC equal to 2 pi r into Hc by Hc minus 2H. This is called SalesBased Rule. The critical current IC decreases with the applied field. If we increase the applied field, that means H, critical current goes on decreases because it is minus 2H. And it will become 0 when H is equal to Hc by 2. When H is equal to Hc by 2, critical current IC becomes equal to 0. If applied field is 0, if H is 0, then the critical current is maximum, that is IC is equal to 2 pi r Hc. Next one is entropy. Entropy means we know that entropy is nothing but measure of disorderness. So here let us see what happens to the entropy in the superconducting state. Entropy decreases on cooling a superconductor below the critical temperature. If the material is cooled below the critical temperature, they will become superconductor. In that state, entropy decreases. Entropy is nothing but measure of disorder of the system. So superconducting state is called more ordered one, because decrease in entropy in superconducting state shows that some of the electrons which are excited in the normal state are ordered in the superconducting state. Then the distance between the electron is found to be equal to 10 to the power minus 6 meter, and this range is called as coherence length. Coherence length. Here you can see Cooper pair. So two electrons are bounded. So this is called Cooper pair, and they are moving under critical temperature. They will move in a particular direction, so that entropy also decreases. Isotope effect. What is isotope? Isotope is nothing but any two substance which has same kind of substance or elements which has same atomic number but different mass number, then that pair is called isotopes. Critical temperature of superconductor varies with isotopic mass. Even though elements are same, with isotopic mass, critical temperature changes. The study of variation of temperature of mercury isotope was done by Maxwell as well as other scientists. It's found that for mercury, critical temperature varies from 4.185 Kelvin to 4.146 Kelvin, as the isotopic mass varies from 199.5 to 203.04. And when relation was given which connects critical temperature and isotopic mass, Tcm to the power beta equal to constant, where Tc is critical temperature, m is the isotopic mass, beta is a constant, and it is equal to 0.5 for most of the materials. And this particular effect shows that current carrying electron interact with the lattice, because number of neutron increases as isotope mass increases, as mass number increases. Persistence current. Now, current can be induced in the ring-shaped superconductor by means of electromagnetic induction. If that ring is cooled below critical temperature in a magnetic field, and then magnetic field is removed, they will become that material will become a superconductor. After it becomes superconductor, the magnetic field is removed. It has been observed that the current continues to persist with undiminished strength for a day. In an experiment, a lead ring could carry an induced current of several hundred amperes for over a year without any change. Such a current is called persistence current. High temperature superconductor. So now all scientists are trying to get superconductor material which becomes superconductor at room temperature. If it is done, all the good conductors are replaced by superconductor because there will not be any kind of power loss. So high temperature superconductors. Until 1986, no superconductors was known whose critical temperature was higher than 27 Kelvin. Next, J. George and Karl Alex Muller discovered oxides of lanthanum, barium, copper, for which critical temperature was 30 Kelvin. In 1987, these two scientists got Nobel Prize for their discovery. In 1987, a particular class of metal oxide ceramics was found to be superconductor at 90 Kelvin. The research done by C.W. Chu and M.K. Wu discovered superconductors at 92 Kelvin. This temperature is above temperature of liquid nitrogen, that is 77 Kelvin. In 1999, superconductivity near 91 Kelvin in the sodium doped tungsten was reported, and this would be the first known superconductor at higher temperature that is not cuprate. Now, a lot of research is going on to find out that magic material which becomes superconductor at room temperature. Superconductivity at 155 Kelvin. So, the group of researchers synthesized fluorinated compound whose critical temperature was minus 118 degrees Celsius. Superconductivity at 200 Kelvin. Recently, some researchers have observed a drop in the electrical resistance. That means they will become superconductor at 200 Kelvin range. It has become possible to fabricate superconducting wire from ceramic material, but its mechanical property was not so good as aluminium. Now it is very important, that is application of superconductivity. Superconductivity is famous because of its application. So superconductors can be used as magnets, but they don't look like a conventional bar magnet. Superconducting magnets. For this, alloys of NB for this alloy of niobium tin, whose critical temperature is 18.5 Kelvin, or niobium titanium is used, whose critical temperature is 8.7 Kelvin. They do not look like conventional bar magnet with two poles, north and south. Superconducting materials are used in the form of wire to make high field solenoid. The material itself cannot be used directly. It acts like a filament embedded in a copper matrix by some kind of material processing. The solenoid then immersed in a bath of helium, and when superconducting state is reached, because the temperature of helium is very less, when the superconducting state is reached, a large current is passed through it, so that it will set up magnetic field of the order 15 to 20 Tesla. Here joule heat is absent, no steady power consumption can be seen, and this type of magnets are used in MRI techniques, that is magnetic resonance imaging. Also, it is used in magnetic levitated vehicles. Lossless power transmission. So by using superconductor, one can expect lossless power transmission because there is no joule heating. Due to joule heating, there is always energy loss during power transmission through any conductor from place to place. But for a superconductor, resistance is 0. That means R is equal to 0, and the power consumption I square R becomes also equal to 0. Next, memory devices. It can be used in memory devices, used as memory devices or information storage in computer. A current impressed in a circular ring of superconductor keeps circulating it over a long period. This property can be used as a memory device in a computer. Maglev Vehicles. This particular vehicle seems the vehicle is floating. Maglev levitated vehicles are known as Maglev vehicles, and here Misner's effect is applicable. The vehicle consists of superconducting magnet at its base. Then the guideway is made up of aluminium material over which the vehicle will set afloat by magnetic levitation. Highly powerful magnetic field, one produced by the superconducting magnet inside the vehicle and the other produced by the electric current in the aluminum guideway, will repel each other. Because of this repulsion, we can see the vehicle is not touching the ground, it is floating. This kind of vehicles are called Maglev vehicles. Squid. Squid is nothing but superconducting quantum interface device. So it is a ultra-sensitive measuring instrument which detects weak magnetic fields. It can measure the magnetic field of heart as well as brain, which has the range 10 to the power minus 10 Tesla, as well as for brain it is 10 to the power minus 13 Tesla. It could be used for logic operations and as memory devices in computers. Superconductors are also used in the manufacturing of electrical machines, generators and motors with superconducting windings. It is possible to obtain high efficiency and small sized by using superconductors. Discovery of room temperature superconductor will bring revolution in the scientific field.